Let me start with a brief recap of what we learned yesterday. And so, well, we learned that a good way to determine the free energy density of a theory is to first compute an effective potential and then minimize it. And then we were doing this for a real scalar field theory. And we computed the 0th order and the 1st order. Yes, so this is where we got. We computed the 0th order and then the 1st order correction to the effective potential. And we got this kind of an expression. But then we, at the end of the day, we saw that there's a problem. Namely, the problem is that we had this, the M effective, which is a function of the shift and of the parameters of the theory, that we saw that if this M effective is small, then somehow this approximation is not really self-consistent. That the 0th order term is of the same order as the 1st order term, and worse still, it's expected to be of the same order as any n order term. And so this means we can compute and we can philosophize as much as we want with this expression, but it doesn't help because there are unknowns that we don't control. So we have to be able to do better. And so that's somehow the goal for today, to show how we can do better. And so, however, before we get there, we take sort of a short interlude. And I'll come back to this formalism. This imaginary time path integral formalism, because that's really then the theoretical tool which allows us to do better. And so it's good to be convinced that it's a valid tool for our problem. Okay, so how can we derive it? How can we prove it? Well, we borrow Feynman's derivation of a path integral. So Feynman says that, and now I'm generalizing already from sort of the quantum mechanics to a field theory, but it's the same. So Feynman says if we have some initial field, and then we evolve in time with the Hamiltonian from time ta to time tb, and then we project on some other field, then this quantum mechanical amplitude can then be expressed as a path integral, where the initial value is the initial value here, and the final field is the constraint that we have here, but otherwise we integrate over all possible fields. And then here we have, instead of the Hamiltonian, here we have the Lagrangian density. So for a scalar field, the kinetic terms and the potential. Okay, I'm using a metric plus, minus, minus in these lectures. So this is then the Lagrangian. So this is what Feynman tells us. Now what we want is something similar, but not exactly the same. So we want to do the partition function. But now the idea is that here is a trace, but the trace is kind of a universal thing. So you can do the trace in any basis you want. So yesterday for the harmonic oscillator we chose the energy eigenbasis because it was convenient for the harmonic oscillator because we know the energy eigenvalues. But here the idea is that now we instead take the eigenstates of the field operator. So we evaluate this trace in the field eigenbasis. So to say we take this kind of fields and then we integrate over all such fields and we take the trace in that basis. So now we see that it's quite similar to the left-hand side here, and in fact we can make it the same if we do a wick rotation, which means that what I will do is now I want to make this the same. So let's say I set TA to 0. But then I need to set I times TB. I times TB, I need to set, I have to divide this by H bar. Now for a moment, I'm keeping H bar not equal to 1, because sometimes it's convenient to see what is really quantum mechanical and what is classical. So, but soon we'll again put H bar to 1. So then I would have to divide this by H bar and then multiply. If I divide by H bar, then I have to, here I multiply with H bar. So this means that I times TB becomes beta times H bar. So that is then fine on the left-hand side. And now on the right-hand side, I do a similar thing. So I will call then I times T. I'll substitute that to tau. And similarly, I dt to d tau. And that's that's basically it. I mean, it feels like sort of like as a silly trick or so, but after all, Feynman's path integral is also kind of a silly trick. You just insert things, and I mean, Feynman just wanted to make it look like nice and classical, the argument there, and so it's a series of tricks, but it's a valid mathematically. There's nothing wrong with that, and so if we now do it, then it follows that Z phi is now the thing to watch out for is that here on the left-hand side we have exactly the same state as on the right-hand side because it's a trace. In original Feynman there are two different states, but here we have the same state. So therefore to the path integral here we have to add this path integral, and that gives us this path integral where we integrate over everything, but with the constraint that at the end, and now our end is at beta H bar, we are at the same position as at the beginning. And then otherwise, otherwise I dt becomes d tau. And the boundary is 0 to beta H bar for the tau. 1 over H bar remains there. Otherwise, everything is the same, except that also in the time derivative we have to do the substitution. So in the time derivative, then I have now, instead of dt, I have twice I, so minus d tau phi, and then the spatial part is minus 1/2 di phi, and then the potential. And this is what we called yesterday is the minus the Euclidean Lagrangian density. So that's really the derivation. So it's really easy, so to say. Okay, a few more things is that usually then we go to, often we go, in perturbation theory anyways, we go to momentum space. So now in this imaginary time, how we then represent fields which depend on this tau and on x's, is that, okay, maybe I should first draw, maybe it makes it easier, I'll draw a big picture. So what does it mean now? Well, that we live in this kind of a space which is compact and which is periodic. Well, it means that we live in a space-time where the spatial directions are just normal. Let me draw just one spatial direction. This is like x. But then the time direction is compact. So actually we can draw it as a circle, because after all we always come back. So we can sort of measure time from, let's say, here onwards. But then we come back to beta h bar. That's the circumference of this circle. And so then it's like we are living like on a tube, as it were, or on a torus if we go to infinite volume. So it's a compact. Time direction is compact. Well, and not only compact, but periodic. Okay, so this means that when we have a periodic compact time direction circle, then the Fourier analysis goes with a discrete set of Fourier modes. And so these are the modes we already saw yesterday. These are the Matsubara modes. And then in the space we do as usual. And then we may represent fields in this Fourier space, where now k dot x is the Matsubara times the imaginary time minus k vector dot x vector. Yeah, so everything is really like before, except that anything that has to do with time is now treated differently. And also then, like propagators, we already mentioned the propagator, but now propagators, in some sense, they are simpler, because if we then take a 2-point function, if we contract, then what is nice about all these Euclidean things is that really everything comes with a plus. Well, here everything is with a minus, but with the minus we take out, and then everything is with a plus. And so also in the propagator, you don't need to remember where to put the minus sign or where to put some I epsilon for a Feynman prescription. There are none such things here. Everything is really nice and positive. Omega n squared plus ek squared, as we had. And then some delta function here. I put here a delta bar because, well, there are some 2 pi's and whatnot, but it's not important for us now. Okay, so that's now the tool that we are using, and somehow the important thing is that in this tool there's nothing perturbative. We are not really doing any approximations here. We are maybe doing some mathematical tricks, but these are not approximations. So all this is valid even on the non-perturbative level. Some people would then take this theory and just put it on a computer and simulate it, and that's also fine. We will do mostly perturbation theory now in the following. Okay, so now we have our tool. So now we come back to the problem and what we can do about it. Okay, so this problem is called the problem we identified at the beginning. It's called the infrared problem. Somehow that's the jargon. Infrared problem of thermal And so it's a very general problem. Actually, it applies not only to the scalar field theory we discussed here, but also to gauge field theories and everything. But it's already present here in the scalar field theory. So again, if we have some field which has a mass which is small, leads to, then this is not a problem for the theory in itself. It's not a problem for the physics. It's just a problem for us because it leads to the breakdown of perturbation theory. And we just like perturbation theory because we are used to it, we can do it to different loop orders. We would like to think that it's a controllable, useful tool, but sometimes it is not. So how can we then, what should we do? So the idea is to whenever you have a problem, somehow you have to try to isolate the problem. I mean, what is really the problem? And then once we isolate the problem, then we can do everything else without a problem. And then we hope that once we have done everything else, then we afterwards concentrate on the problem. And maybe in the meanwhile, the problem has become simpler, or we've thought about another method or something. But let's postpone the difficult part till the end. That's kind of the good philosophy for life. Let's postpone problems. So isolate problem and solve it afterwards. So how do we isolate the problem? The isolation, the observation is that if we have this small mass, then this small mass is really small if we compare it with this, well, for instance, with 2 pi t. It's even smaller if we take a square of that and compare it with 2 pi t squared. So why is this comparison relevant? Well, it's relevant because it's what appears here. So these were the Matsubara modes. These are 2 pi n times t squared, and epsilon k squared is k squared plus m effective squared. So now we see that if I have here a small number, but if I have here a large number, then it would not be a problem. I mean, a small number kind of shielded by a large number is not a problem. It's only a problem if we don't have here a large number. So it's only a problem for the Matsubara zero mode. And so in this kind of a situation where we isolate a particular mode and say that that's the one which is problematic, then the tool is to is the concept of effective field theories. And so we write down effective field theories, and somehow it's a long word, so we usually call it EFTs. So write down EFT for n equals 0 modes. Then we effective field theory is a general theory which has many parameters. We determine the parameters by, as we say, integrating out all these modes which are not problematic, so unproblematic non-zero modes and then again look at the dynamics of the EFT. By other methods that we then probably cannot do with perturbation theory, then we have to use something else. So that's the idea, and so now in this particular context, this EFT construction has a name, and so EFT known as dimensional reduction often abbreviated as DR. Why is that? Well, the reason is that we had this circle, our fields live on this circle, but if I now take a field which is a Matsubara zero mode, then its dependence on the, if it's a zero mode, then omega n is zero, then it doesn't depend on the Tor coordinate. So therefore these fields, these omega n zero fields, they live in one dimension less. They just live in this world. They would just live on a line, and so that's why we have one dimension less. So now for those, well, for some people in different backgrounds, this concept may be very familiar because, I mean, in the history of physics, this is also known as the Kaluza-Klein reduction from 100 years ago when people were thinking about unified theories and unifying gravity with other theories. So the whole idea that one has a small compact direction is from there. And so in this sense, the tools that one can use in this thermal context, they are kind of classic tools. With the difference that here now we start with a four-dimensional theory and then we go to a three-dimensional reduced theory. Whereas with Kaluza-Klein, one starts with maybe 5 dimensions or 6 dimensions, and then one reduces to 4 dimensions. Okay, so that's the idea. Now we should implement this. And so the implementation simply starts by kind of writing down the most general effective action, say, for our effective degrees of freedom, which are now these zero modes. So they live in this world of 3 dimensions. And then we can ask what we can write. Well, first we should note that here originally we had, I mean, in the original theory we had 1 over h bar integral 0 to beta h bar of d tau. But now, since nothing depends on this tau, these effective fields don't depend on the tau, then we can just carry out the integral. And then it's a trivial integral, and it gives beta. Beta is 1 over temperature. So that's also just fine. It's like in the Boltzmann weight. It looks like classical statistical physics. And so there's nothing to be, just really sort of, it is kind of classical. One sometimes also calls this a classical approximation, precisely for this reason. It looks then like classical statistical physics instead of quantum statistical physics. But the quantum effects are all there in the step where we integrate out the other modes. And so what would I write here? I write here, I can start by writing exactly the same as we had before, but now I should call the fields, they are not exactly the same fields that we had before. They are somehow related, but there can be some, the field, the normalization of the field also can also be affected by integrating out this other mode. So I write di phi 3. Phi 3 is now my 0 mode living in 3 dimensions. And I don't have any time derivatives exactly because nothing depends on time. Then I would write a mass parameter, but now it's some different mass parameter, effective mass parameter. I can write a coupling. And so far everything is fine. I've done nothing but basically taken the previous structure and renamed things. Well, the difficult and kind of the key part in effective field theories is always that it doesn't stop anywhere, basically. You should have everything here, all kinds of higher dimensional operators of any power. Of course, when they are higher dimensional, they have more powers of the field or more derivatives. Then just by dimensional reasons, if you have higher powers of something upstairs, you have to compensate by something downstairs. And what one compensates by is then, let me write it sort of schematically as some derivatives din fields phi 3 m. One has to compensate. If n plus m is more than 4, then there will be some, you have to divide then by some powers of, and powers of what? Powers of the scale that one has integrated out. So basically 2 pi t to then some power p, let's say p, which would then be positive if these are large enough. And so then one sees that, okay, you have all these operators, but if one is then looking at fields which are, let's say, which have relatively low momenta, or the expectation value of the field is not exceedingly large, then these operators are suppressed. So these are just words, and of course, sort of the hard work of the problem is to really prove how much suppressed these operators are. And that hard work we will not be doing today. But in this context of the dimensional reduction, it has then been analyzed, and so one knows that these operators, they give a contribution which is very small in the theories which we are normally considering. Okay, so far we haven't really done anything, and then what we have to do is to determine these parameters. So here I call this integrating out. Or often one also calls this matching. So matching, what does matching mean? Matching means here that we are matching our effective theory to the original theory. The original theory is the correct starting point. Now we write an effective theory, and we have to match them, these two theories. We have to match the parameters such that really these two theories give the same predictions. We cannot just take some arbitrary values. So now I think the best way to to do this is to somehow, just graphically, let's try to illustrate what it means. So, so now this, okay, so what we have to remember is that at each vertex, energy is conserved. So this means that if I had different lines entering a vertex, then the sum over, let's say, over the Matsubara frequencies of those fields has to also, they have to add to 0. This is now the statement which in Minkowskian space one would say that the energies entering a vertex, if one draws the lines in the same direction, energies must match. Total energy is not created out of anywhere, so total energy is conserved. With Matsubara modes, one can say that the Matsubara modes have to add to 0. And so this means that, for instance, if I take now a vertex, here we have a vertex for fields, then okay, it's possible to have all fields have 0 modes, that's a vertex. But then I can also have 2 of the fields have non-zero modes. And I now draw the non-zero modes with a solid line. That would be a vertex. You have to have 2, you cannot have 1, because if I had 1 non-zero and 3 zeros, then it wouldn't add up to 0. So I have to have 2, then the non-zero mode can somehow come in and go out, and everything is fine. Of course, I can also have then, I could have other vertices where I have just 1 zero mode, and maybe 3 non-zero modes, or I can have 4 non-zero modes. This type of vertices I can imagine. And so now we can then look at what kind of diagrams we should compute to determine the parameters. And so the simplest thing is the mass parameter. So what we then compute is, well, mass appears in a 2-point function. So we have to compute a 2-point function. So the 2-point function would be just like this, that I take one of those vertices, and the simplest one I can take is this one. That now gives a contribution of the non-zero modes to the propagation of the zero mode. So that has to be accounted for in the matching. Of course, I also have a vertex which has 0 mode here in the loop, but that I don't need for the matching. I mean, that is the dynamics then of the 0 modes, and that I'm postponing till later on. So at this matching stage, I only need to consider diagrams where there is at least one non-zero mode. Those I have to treat now, and then the difficult dynamics of the 0 modes I treat later on. For the lambda 3, it's a 4-point function. So then I would take, for instance, a diagram like this. Like a loop. Okay. So far it's all fine. But of course it doesn't stop there, and so this is sort of one loop. And so somehow it becomes a lot more interesting. And also a bit tricky at 2-loop level or higher. So let me just illustrate what is the issue here. So suppose you want to compute corrections to M3 squared now with 2 loops. Okay, so we could draw diagrams, and so there are some simple diagrams we can draw. So for instance, if I take once this loop and then I attach to it another loop with a non-zero mode, then for sure this I have to compute, and that's part of the contribution of the non-zero modes at 2 loop level to the value of this. So all fine. Now, however, let's consider the following diagram that I have here, 0 mode, and then I take 2 of these diagrams and I make a loop out of that. So now, why is this confusing? Well, it's confusing because there's also a 0 mode here inside the loop. So should I account for that or should I not account for that? So now, if I was not sure, then I could start drawing. I could say, okay, this is just these are symbolic things. I can pull the lines where I want. So I could draw. For instance, I could pull this line up. So let me pull this line up. Then I would have a loop like this. Well, how is it different? Well, it's different because now I could say, wait, this looks like this. So I could say that I've already accounted, perhaps I have already accounted for this, because I already, oops, no, not like that, but after all, I already computed this loop. So I computed how the non-zero modes are affecting the coupling. And then if I would compute with the modified coupling a one-loop diagram within the effective theory, then it looks precisely like this. So then I may be wondering, am I now doing double counting if I also am computing this? So this is sounds like a simple issue, but actually this is a very, very tricky issue. One has to be, if one knows how to handle this, then one can do anything with effective theories, basically. And the point to understand is that when we compute here, then there are also momenta. I can put here some momenta, like P1, spatial momenta. The Matsubara zero modes, they have still spatial momenta. I can put spatial momenta there and here and here, and the total has to be conserved. But, okay, if I put the arbitrary spatial momenta, then this is a complicated function of, let's say it's a complicated function of these momenta. But this coupling is just a number. It's not a function. It's just a number. And so now the way to extract the coupling is by expanding in momenta. So in this whole thing, maybe the notation, this was just some function. This was not my phi field. This was some function. It's a complicated function, but now in principle, I could expand it. And so the first term, where I put momenta to 0, that would give my coupling, and then there would be corrections of order p squared, pi squared. And so this would contribute to my coupling. And these higher powers, what they do is then they add, powers of momenta in momentum space, they correspond to derivatives in configuration space. So if I have p squared and a 4-point function, this would mean that I have like phi to the 4th, but then with derivatives. So it would be one of these higher dimensional operators, sort of, let's say di phi 3, di phi 3, then still phi 3 squared. And so this is how this momentum dependence generates these higher dimensional operators. Okay, so but if I say that, then I may get even more confused. Now I can say that, okay, I have this loop, and so first question, is this not in lambda 3? Now we know one answer, not necessarily, because this loop also produces higher dim operators. But then in the second step I could ask, well, if I keep some of these higher dimensional operators, and if I show that they don't have an effect, then again, am I not safe? I'm aware of this fact that there's something else in the loop, but I've analyzed that, and it should be fine. But it's still not fine, and that's the difficulty, because not all expansions converge. And typically what we are expanding here, when we are expanding in momentum, we have some propagators and we are expanding, but the expansion of, the geometric series, expansion of 1 over 1 minus x, or 1 over 1 plus x, the convergence radius is not infinite. So you can only expand when x is small. Absolute value of x is smaller than 1. And so therefore there's an issue of taking the limits, basically. So that's could be, but not. But the bigger issue is some limits don't. Well, one can say it like that. Some expansion doesn't converge, or in other words, some limits don't. Limits are not interchangeable. And this now became very complicated, but let me try to summarize now it in a simpler way to say what really is the issue. The issue is the following, put another way. I will draw the diagram again. I will try to make it larger so I have some space to. Right, and so here are the non-zero modes. It's clear that these I have to integrate out. Here I have the zero mode. If I'm computing, say, the mass as I wanted to compute here, then I can put here p small. Say, I can even put zero momentum here, all fine. But the problem is that this guy here can carry momentum. And even though it's a zero mode, it can carry a very large spatial momentum. And if the spatial momentum here It can be small, much less than the scales we are integrating out, but it can be, or it can be large. And if it happens to be small, the part of the integral where this is small, that's where everything is fine. Because if it's small, then it corresponds to a Taylor expansion. That part of the integral is accounted for by the lambda 3 and by these higher dimensional operators. But there is also a part of the phase space where it's large, and this we cannot forget about. And this we cannot reconstruct even if we consider all higher dimensional operators. It has to be separately accounted for. So this means that at the end of the day, what we really have to do is normally we cannot kind of decide in advance whether it's important or not. We really have to compute this diagram kind of exactly in the full theory and just look at what comes out, including all the momenta. And then afterwards we decide, we look at the result and we decide where can we put the different pieces. And so here the upshot is that there are many, well, there's a contribution. There is a new contribution to just the mass from these hard momenta, large momenta. And there are other terms which just reproduce effects from lambda 3 or higher dim operators. And these are the contributions from them smaller momenta. Okay, I didn't want to kind of make it look frightening. I mean, it's not frightening. I tried to make it just to show that it's really kind of even this, so to say, simple part where we are integrating out something that we know and something that we can handle in perturbation theory. It's kind of, if you wish, an intellectual exercise. I mean, one has to do it. One has to sit down, think about what one is doing, do it correctly. But nowadays we can do that, and there are people have done this kind of computations not only to the 2-loop level as here, but to the 3-loop level and so forth. And we can really, in principle, we can go to any order, and we know how to handle it. So all is fine, but it's not trivial. But nowadays we know how to do it. Okay, so what I want to do next. So let's put here small end of a subsection. And so what I want to do next is we want to go back just to the one loop, and I want to show how we compute that. I just want to show some explicit computation, also because it's a nice little computation. And I think we will do it after the break, but let me, what we can already do is I can draw some contractions. So how would I really then compute this? I have here a vertex and I want to compute a 2-point function. So the way I would do this is first I put here 2 phi's. Now I don't put here phi 3 because these are, so to say, the phi's of the original theory. So these are kind of the external legs here. And then I put here this vertex. And so this vertex was lambda over 4. And then there are 4 fields here. And then I do contractions. And so that's just a nice way of counting. How many times can I contract? So I can take this field. And all of these are equal. I can contract therefore 4 times. And the other field, there are still 3 left, I can contract 3 times. And then I'm left with 2 free, so to say, two leftovers. And the leftovers are these ones. They then contract them among themselves. And so now what I learned from here is that I get a contribution to this mass, which is 4 times 3, 4 cancels against 1 over 4, so it's 3 times lambda. 3 times lambda, and then there is this loop. And this loop is now, the loop is exactly, well, it's 1 propagator. And then it's a loop, so there's an integral, some integral over the momenta. And the only thing I have to watch out for is that I'm only integrating out the non-zero. So actually I have to remember it's not all of them. Omega n has to be non-zero. Now, maybe I was too fast. I went directly to the one loop. I mean, to check that this is really, that I'm getting the right thing. I could have also checked that what I really want is, at the end of the day, I want to be sure that what I get from these contractions is the mass. So I should have started just by putting this mass operator, doing the same contractions, then I get 2 and 1. And in that case, there's no free loop left. And actually, if this was my original theory, the mass came with a minus sign, so it was the minus. So from here, from the tree level, I would have gotten just minus m squared. That was the tree level mass. And now we get the loop. Okay, good. So now I think it's a good moment to take a break, and so we start a 1/4 and then we do this sum integral and see what comes out. Okay, I guess we can continue. So yes, I wanted to compute this loop. And so now we found out that this loop gives a contribution which is 3 times lambda, and now sum over, well, d times sum over omega n not equal to 0, and then integral over k, and omega n squared plus k squared plus, let's say, m effective squared. Well, this is a bit, depends a bit on what we are computing. Let me just write m squared. Actually, I will even omit this now for simplicity, because after all, we are integrating out the non-zero modes, and we said that for the non-zero modes, whatever it's m effective squared or not, it's not a problem. It's shielded by these large values of the omega n. So we'll omit that. Okay, so now, first step, change order of integration and summation. Well, that was easy. So now we have this sum. Well, now yesterday we were discussing this sum, and actually we know this sum. We did it yesterday. We saw it even from the harmonic oscillator. And now if I have here just the k, then this sum is what it is. It was this 1 over k. Well, then we had 1 over epsilon, but now instead of epsilon I have just k. because the mass is 0. And then there was 1/2. And then there was the Bose distribution. Well, this would have been the sum if we had summed over all Matsubara modes. But now we have to omit the Matsubara 0 mode. So, but I can still take the sum and I just subtract the contribution of the Matsubara 0 mode because it's simple. It's just d over k squared. So not so hard to do it correctly. So that's now what we would have to do, this kind of an integral. Okay, so now I kind of go here to have a bit more space, because what I need to do now is I need to write down the integration measure for the spatial momenta. And so now we are doing a loop computation. And so, you know, in field theory, loops are normally divergent. And so you have to regularize somehow. And so the most convenient way to regularize loop integrals is this dimensional regularization that we write, okay, the 3 lambda. Okay, now I still first write. So we kind of consider the integral in d dimensions. And then 1 over k, and now I put everything inside. Now it's only k because I pulled out k here. Okay, where now the d, the dimension of space-time, is treated as a complex parameter. So of course, mathematicians will normally get very upset at this stage, because they think about geometry, and geometry is geometry. You cannot make geometry kind of complex dimensional. But for us, it's not really geometry. We talk about integrating in space, but we're actually not talking about geometry. We are talking about the theory of integration measures. And integration measures one can define more generally than referring to a particular geometry. And now, in this case, we can simplify this integration measure a little bit, because the integrand depends only on the absolute value of the vector. And so now I will just write here without proving this, but I will write what this measure is when you integrate over the angles. So then we are left over with the radial integral, and then 2 times dk k to d minus 1. Well, the dimensions have to match. It's a d-dimensional integral k, so in total there have to be d powers of the variable. And then there is, from the downstairs, it turns into the following. There I had 2 pi, now it becomes 4 pi d to 1/2 and gamma d 1/2. This is the Euler gamma function. This kind of measure, again, maybe at first sight a little bit scary, but not really, there's nothing to be scared. I mean, these are elementary functions and measure, and then d as a parameter. And then we have 1 over k, and once again the integrand, and now I take the first term first, well, the middle term first, k to k over t minus 1, the Bose distribution first, and then I have the other terms 1/2 minus d over k. So now there's a wonderful thing about dimensional regularization. I mean, basically that's why we do it, more or less. Well, okay, we do it first of all because everything can be done analytically, but second because there are many terms which drop out. And so basically, well, not only basically, but in quite concretely, any term which is we say has no scale, but what we mean is that is a monomial, is a power, positive power or negative power. But like here's a negative power, well, a second negative power, here is a constant, it's also a power. Any power, but doesn't have any scale. I mean, this has a scale because there's a number 1 here. So you can minimize or maximize this function. You cannot if you do a rescaling of the k, it doesn't go, you cannot pull anything apart because it's inside the exponential. But here you could, there's no scale. And if there's no scale, then in dimensional regularization one can prove that everything integral is 0. How does one prove it? Well, one simply rescales the integration variable. And since there is no scale, then the rescaling, it comes in front of the integrand. But then the integrand, well, basically it just looks the same, but you have rescaled it. And then the only way it can be the same with after rescaling is that it's 0. Well, this is a bit too short, but that's roughly speaking how it goes. There's no scale integrals are 0. So that's why dimensional regularization is so convenient. Well, this one is the one which gives a contribution. So here what we do here is we do the following. We rewrite this. Actually, we rewrite it as we first saw it. We first saw it when we got it from the harmonic oscillator. There was an e to minus k over t upstairs, and then I had 1 minus e to minus k over t downstairs. And now I re-expand this again in a geometric series. And so then it's a sum n. Well, if I didn't have anything upstairs, it would be a sum of from 0 to infinity and powers of the exponential. But now I have 1 power upstairs, so then it becomes a sum from 1 to infinity e to minus k n over t. This I do here. Okay, so let's now be what have we got? Now I pull the summation maybe here in front, and then I have some factors which I can also pull out here. These trivial factors, and then I have the integral dk, and now there's a division by 1 additional k here, so it's k to t minus 2. And then there are these factors e to minus k n over temperature. So this should now look kind of familiar. It's almost a defining integral of the gamma function. And we can make it look like the gamma function by now rescaling variables. So let me denote by x, then k n over t, and then therefore k is x t over n, and dk is t over n dx. I rescale variables. So then I get 3 times lambda sum n1 to infinity, 2, again always the same part. And now what we get from the scaling is here I have once dk, and then I have k to d minus 1. And these are both scaled in the same way, namely by t over n. And so in total then d minus 1 plus 1. So d minus 2 plus 1, so d minus 1. So I have to put t over n to power d minus 1. So I put here t to d minus 1, and I have n to d minus 1 downstairs. And then I'm left over with integral 0 to infinity, now with dx, x to d minus 2, here it's still d minus 2, and e to minus x. And what this is the gamma function of d minus 1. So gamma z is integral 0 to infinity dx x to z minus 1 e to minus x. So in the definition of the gamma, there is this minus 1. I have to take out 1 minus 1, and then I have gamma d minus 1. Okay? Now I'm almost done. Here I have gamma d minus 1. Here I have this still this sum, but now after there is scaling, the n appears in a very simple way only here. And 1 over n, sum n1 to infinity 1 over n to x is what? That's the Riemann zeta function. So this is zeta of x. So what have we got? We have 3 times lambda, 2 times d to d minus 1. Then from the sum, zeta d minus 1. From the integral, gamma d minus 1, and then downstairs 4 pi d half gamma d half. Yeah, I mean, I just like to, these are kind of these nice expressions, and sort of what is characteristic of thermal field theory is that you get Riemann zeta functions. So if you do some similar integrals in vacuum field theory, you always get gamma functions. These kind of ratios of gamma functions or multiples of many different gamma functions with arguments like these, d minus 1, d2, whatever. This is kind of vacuum part, and the Riemann zeta means that you are at finite temperature, basically. Okay, so now what we do then afterwards, we do everything in d dimensions for as long as we can, and then we are at the end, and everything is still completely general, and then we have to put d equals 3. We substitute d equals 3, and so then we get 3 times lambda, 2 times t squared, zeta d minus 1 is 2, gamma 2, 4 pi to 3 halves. Let me write it as 4 pi times the square root of 4 pi, and then still gamma of 3 halves. Okay, so now, well, I don't know, in the old times one would have looked in the book. Now maybe Mathematica tells you what gamma 3 halves is. It's 1/2 of gamma 1/2. Gamma 1/2 is square root of pi. Gamma 2 is the same as 1 factorial. 1 factorial is 1. And the more, well, interesting part is then the zeta 2. And zeta 2 is pi squared over 6. So we substitute these things. What we get is then 2 times t squared pi squared over 6 divided by 4 pi, 2 times square root of pi, 1/2 times square root of pi. And now if we've done everything correctly, it should be a nice expression. So square root of pi times square root of pi is pi, in total pi squared. That cancels against pi squared. Then I have 2 times 1/2, that also cancels. I have 2 divided by 4 is 1/2, and t squared, and 1/6. So 3 lambda times t squared, 1/2 times 1/6 is 12. T squared over 12. This t squared over 12 is somehow a very famous number here. It's this, the value of this sum integral with one propagator. And it's related, yesterday we saw in the expansion of this function ft, the second term, the quadratic term, was m squared t squared over 24. Okay, it's not 12, it's 24, but actually it was a different integral, and they are related. So in fact, this t squared over 12 corresponds exactly to that m squared t squared over 24. And if I multiply, I get lambda t squared over 4, And if you remember, that was exactly the thermal mass we got yesterday for this scalar field. And so it's correct. It's correct, but now we got it much nicer somehow, really from like doing a nice little computation of an honest one-loop diagram. Okay. So that we could do. Okay, so now I kind of take a jump, so to say. So now in principle, we have now learned how to deal with the scalar field theory. But the scalar field theory, well, it's very interesting as a theoretical playground, but it's not really, okay, it is also very relevant for some systems in statistical physics maybe, but it's not really relevant for like real world cosmology as we would like to do. So I now then kind of jump to the standard model, and now very briefly first summarize what happens with the standard model, and then we go to beyond the standard model and do something more, maybe more interesting even. So, but first standard model. So dr, dimensionally reduced EFT for the standard model. So what we have to do then is, we had this real scalar field, and now it's then replaced by the Higgs doublet. Well, I still denote the Higgs doublet by phi 3, but it is now it's a complex doublet, two complex numbers. But otherwise, things are pretty much the same. So, or some parts are the same. So I can still, the principle is the same. We write down the effective Lagrangian, and now the difference, I'll leave some space here. Difference comes that the Higgs doublet is not neutral. It's charged under gauge groups. So instead of the normal derivatives, we have to put here covariant derivatives. And then since it's a doublet, we put here a dagger as a complex doublet. But then the mass term is basically the same, but with complex fields, one conventionally normalizes them differently. So without these factors of 1/2, so then it's just phi 3, dagger phi 3. And then there's again a coupling lambda 3, phi dagger phi squared. And again, there are higher dimensional operators. And now since standard model is the real world, then these have been really kind of looked into, and we know exactly what they do, and we know exactly that they are not important for establishing the phase diagram of the standard model. And what is now missing is that since these are covariant derivatives, so there must be gauge fields, and so the gauge fields have to be added. And so again, once we are in this imaginary time, gauge fields are also particularly nice, look very nice, because again there are no minus signs or nothing. So there's 1/4, let me call it GAIJ, and 1/4 FIJ. This is the weak gauge group, and this is the hypercharge gauge group. In the standard model, there's also the strong gauge group, but the Higgs field is not charged under QCD, So therefore QCD is not playing a big role here. Actually, it's a good question whether you still could add here a QCD gauge fields as well, because in principle there can be some higher dimensional operators where there's also an indirect interaction of the Higgs with the QCD. Well, in fact, there are such things, like Higgs can interact with quarks and quarks can interact with gluons, so there must be some loop effects. But again, they are part of these higher dimensional operators, so they are not that important. Okay, there's one issue which I should maybe mention sort of in parentheses. Well, let me put it as a question. Q. Why no like for SU2, why no zero component of the gauge fields, or for the hypercharge, why no zero component of the hypercharge in LE? These are the zero components, but I mean zero components, they can't be constant in time. There's nothing which prevents that. So somehow they should appear here. And it's a good question, and there's an interesting answer. And we hope to come back to that interesting answer in the very last lecture briefly, if we have time. But I can already tell you that these guys, in principle, they are there. But then if one does a loop computation like that, actually they develop a mass. They become kind of massive fields. Not quite as massive as these 2 pi T modes, but still more massive than the Higgs field or the spatial gauge fields. And so they are still kind of heavy fields. And so one can, again, heavy fields, one can always integrate out. In this case, since they are not quite as heavy, it's maybe not a priori, it's not quite clear how accurate this integration out is. Because again, if you integrate out something, you generate high dimensional operators, you would have to estimate how large the effect is. But again, this has been looked into, and so we know today that this can be integrated out with good precision. Okay, so now we have done what we have done now is we've done sort of what we could do. We've integrated out the non-zero modes, and then we still have this theory, and now we should study its dynamics. And so now we are in a situation today where we really don't know of any other way to study these dynamics of these infrared modes well than by numerical simulations. There are some attempts at doing some kind of renormalization group things and all kinds of all kinds of attempts, but more or less these are typically such that one knows the answer in advance and then one tries to cook up something. So there's really nothing which would have been convincing enough in advance of the numerical simulation that anybody than the authors would have believed that it was the correct way to do it. But simulations of this theory are not too complicated because this theory lives in 3 dimensions, and simulations of field theories are typically they are difficult if there are fermions. Somehow fermions are hard for simulations, but there are no fermions here. That's another story which I haven't been discussing, but fermions, they have anti-periodic boundary conditions across this compact interval. This means fermions always have non-zero Matsumara modes. Therefore, all fermions can be integrated out. All quarks, there are no quarks here anymore, even though standard model has quarks. So it's not too difficult to simulate, and let me just show what comes out. Okay, so maybe 80. Temperature, I now put temperature on this axis. And sort of historically, people put here a Higgs mass on this axis. Because after all, Higgs has not been known for a very long time. So I'll start the axis with 50 and 70. Well, maybe I should make more space. So let's put 70 here, 90, 110, 130. And so what one finds when one does simulations is the following. There is there is a line of first order transitions comes from here and then it kind of ends about here. It's exactly the same type of line as we saw with water, critical point, second order. There are first order transitions here. And then the real world is where our cosmic trajectory is somehow here. And so in the early times when the Higgs was not known, Higgs mass was not known, Higgs had not been discovered, there were times where people thought that Higgs could be 40 GeV or something, and then one could have had a first order transition, and that was very exciting. And those were the times where people were developing some of the theoretical tools that we are still using today. So it was not wasted effort, but it just doesn't work in the standard model, because then Higgs mass increased, and finally, well, already at some point we knew that there is no first order transition, and then finally we know that we are somewhere very far from a first order transition. There's just what we call a crossover. Crossover is if somehow we go from some phase which we like to call the high temperature phase, we like to call it the symmetric phase, because somehow in textbooks often one says that the gauge symmetry is restored, Higgs mechanism goes away. The language is not sort of more field theoretic people don't like this language, because gauge symmetries are actually always existent, even in the what we call the broken or the Higgs phase. But anyway, that's why I don't like to call it a broken phase, because some people don't like to say that the gauge symmetries get broken, so it's better to call it a Higgs phase. So Higgs phase is the phase where the Higgs phenomenon is active. And so that's the story for the standard model. And so in the standard model, we don't have a first order transition. Okay, so now let's end the lecture by doing something where we can have a first order transition. And so fortunately, it is the case that one doesn't need to modify the standard model by very much, and one can already change the transition very much. One can have a first order transition. And whether then nature makes use of this possibility, that's a question for. Sorry. Yes. No, I'm confused. Yes, very good. Yes, so thanks. Yes, I was a bit confused. I didn't completely realize, but it's okay. So I'll just take 2 minutes. So what we can do is the following, and so we can modify the theory by, well, we can take a theory where we add some additional scalar field. And now the way one can do it is one can choose this field such that both symmetries like to get broken. And then we add some interaction between these fields. And now we can play exactly the same game as we did. We can compute the effective, well, the three-dimensional effective theory. We can compute the mass parameters. And the idea is the following. We can arrange things such that, let me draw here the chi direction and the phi direction. And the phi is now what we want, is kind of our Higgs field, and the chi is the extra field. And so the idea is that we arrange things such that actually this symmetry gets broken first. So we jump from symmetric phase to this phase first, and that's the second. That would then be a second order transition as we normally have with scalar field theories. But then we can arrange things such that at very low temperatures, still the physical minimum, well, that the minimum in the phi direction would be preferred. So there would be another minimum here. And now one can arrange things such that this, okay, there's like a valley here, there's a valley here, and these small ticks are where the water flows. So it's a deep valley here, deep valley there, there's a maximum here, and then there is another hill here. So it's like a classic saddle point. But with these two scalar fields, it's not a problem if these two transitions are very weak. One can arrange things that this is a weak transition, but then at the end of the day, you would have to go to the other valley, and then you have to cross this saddle point. And so this can be then made into a first order transition. And so one calls this a two-step transition. And so it's a very simple modification of the theory, which allows you to build in a lot more structure. And then it's ultimately like a question for experimentalists if such another scalar field exists. Okay, good. So that's it for today then. And so tomorrow we then assume that there is something like this. Actually, there is a first order transition in the universe. And then we see how it would really proceed in real time.